In his book, Szent-Györgyi shared a discovery that there are many types of ice in our body, which may come as a surprise to some. To date, more than 20 types of ice made solely from water are known. Although all of these ices are made from pure water, they are different types. Another type of ice is known as hair ice, which appears as thin threads on wood rays and never on the bark. Here is Szent-Györgyi's thoughts on the strangeness of water. Quote, "When considering water structures, we enter a fantastic and fascinating world. Bridgman, in his studies on high pressure, could distinguish between half a score of different ices. But we need not go to ice to find structures in water. Bernal and Fowler showed water to have a quartz-like crystalline structure, which is different from that of common ice. The situation becomes more complex still if we consider water structures built around solid surfaces. The tendency of building structure-ordered layers around surfaces running deep into the fluid phase seems to be a general tendency of liquids. All this put together means that water within the cell may not be random water, but liquid ice. No attempts have been made yet to apply our knowledge of water structures to living systems. Living matter seems to be a system of water and organic matter, which forms one single inseparable unit, a system, as the cogwheels do in a watch. Water is not only the mother, it is also the matrix of life on Earth, and biology may have been unsuccessful in understanding the most basic functions because it focused its attention only on the particulate matter, separating it from its two matrices, water and the electromagnetic field." End of quote. These layers of ice were found to be several microns deep, and the building of lattices means long-range order, in which the single molecules will collaborate collectively as one organism. So one of the ice's roles is to create structured ordered layers in a mass of water. This also refers to the idea of a water mass containing protected or walled cells that are made entirely of water. These boundary layers in water are similar to sheaths found within plasmas. All plasmoids have sheaths enclosing them too, which helps them maintain their identities. But there is more to it. This long-range order and the single-molecule collaborative effects he described were also researched by David frank-kamenetskii, Soviet scientist who developed the thermal explosion theory and worked on plasma physics problems. He talked about this topic back in a 1961 publication, which then mysteriously vanished from all subsequent editions of Proceedings of the USSR Academy of Sciences and its English reprint version. In his article, frank-kamenetskii wrote, quote, "One of the essential characteristics of living matter is a certain degree of ordering of the microstructure. Analysis of a number of experimental data says that water in the body at temperatures above 0 degrees is partially structured, meaning the arrangement of its molecules manifests to some extent a long-range order. The ideas about collective levels of semiconductor-type excitation are becoming increasingly widespread. Excited electronic states play an important role in the accumulation and migration of quantized energy in the body. But if initially they were understood as excited levels of individual molecules, further studies then clearly indicate in favor of collective levels. Such collective levels arise in the presence of long-range order. The question of the long-range order in living matter is of a deep fundamental interest. The analogy with semiconductors allows us to hope that collective excitation levels and energy zones of the semiconductor type are a more general manifestation of orderliness. The orderliness we postulate is specific to living matter, but it would be even more important to find experimentally an orderliness that disappears after death. The existence of such zones is also important because new biological effects can be expected from them." End of quote. So, can this specific to living matter long-range order then be a key to a fundamental understanding of what life is and how it emerges out of non-organic matter? He also noted that the structures like semiconductors in living matter can demonstrate phenomena similar to electron plasma in a gas discharge. and the presence of plasma and ice, as previously demonstrated by Szent-Györgyi, then can spontaneously self-organize structures that support long-range order in all living organisms. This discovery adds a new dimension to the argument. But why do we need so many different types of ice in our body? And how does it help to create long-range order and collaborative effects in a living matter? A hint can be found in the phenomenon of criticality. This phenomenon can help to explain why many complex systems, such as avalanches or our cell networks, suddenly behave in new ways and gain new abilities. And such critical phenomena arise in transitions. The idea is that if the system is just on the edge of the order and disorder and goes through the phase transition, such as water changing from ice to liquid, the system moves through what's known as a critical point. In a moment of transition from one phase to another, exotic properties emerge. And such small change in the critical variable leads to drastic changes, almost discontinuing changes in the function. A simple magnet can demonstrate critical dynamics. Atoms in the magnet can have spin directed either up or down, with all spins pointing in one direction when the magnet is very cold. When heated, the spins start to move, change direction, and cancel each other out. This causes the magnet to fall off the metal surface, indicating a transition from being ordered to disordered. During this transition, clusters of similarly oriented spins form throughout the magnet. In 1987, physicist Purbach proposed the idea of self-organized criticality, where many complex systems in nature may organize themselves around critical points. To explain his theory, Bach used the example of a sand pile. When the sand pile gains enough mass, the grains of sand can no longer stay in place due to friction. Adding a single grain of sand to the pile will trigger an outsized effect, causing avalanches to cascade down the sides of the sand pile. Similarly, natural systems self-organize around critical points without needing tuning. Examples include various complex systems where long-range order is needed. In the body, these systems may operate slightly subcritical, meaning they approach the critical point but then push away to avoid danger. The different types of ice mentioned before, hence, can help to fine-tune the matrix where these processes can occur then. Uno Capvilliam, Soviet physicist, in his little-known article independently came to similar conclusions. He wrote, quote, "Life can be imagined as an avalanche process in a very complex biological resonator, feeded by some source of potential energy. The main avalanche, which coincides with the lifetime of the organism, consists of myriads of sub-avalanches in elementary resonators of the system. Interestingly, the initial conditions of the avalanche launch, precisely the state of the universe at the moment of birth, play, according to the theory, an important role in the unfolding of the dynamics of a living system. The active elements of these resonators are cell membranes, which consist of giant molecules, mass dipoles. These processes are very vulnerable to the effects of external fields, but nature has provided protection against them. Calculations show that systems of giant electric dipoles and membranes can be receivers of ultra-weak physical signals at or below the level of quantum noise. These possibilities of living organisms have not been studied at all. They may be the sources of anomalous phenomena that have not yet been explained." End of quote. He further wrote that the geometry of the resonator network and nerve branches can be fractal, like a Sierpinski carpet, an idea that has a direct connection to the physics of criticality. Such structures do not tolerate empty space. The change of just one unit leads to the rearrangement of all its links. Such a mechanism ensures the variability of a living system with small disturbances when a certain place is prepared in the structure to react on a trigger. Interestingly, a quantum biological model that Capvilliam described can be implemented from various materials. Theoretically, such living systems can exist in any form and can be ultimately non-organic, meaning that such life form can change beyond recognition. Therefore, theoretically, there may be living systems on Earth that we don't know anything about. The latest experimental results in biology shows that a man is not only a purely biological construct, but that bioelectronic, biochemical, and informational processes also play a role. Today's theories are based on a profound vision of Szent-Györgyi. It was he who first realized the importance of the intricate and dynamic structures that can naturally arise from materials such as ice, water, and plasma. But in order to understand the implications of his research and see how it works in practice, we should look at superconductivity and Josephson junctions first.